Alright guys, how's it going? We're going to be doing maximum product subarray. Off this stream, I redid coin change, so I understand the bottom-up dynamic programming approach better. Pretty good. I feel like, these terminologies like overlapping subproblems and optimal substructure mentioned by someone in the previous stream, I want to look into these still and understand them so that I can use these terms myself. So I might just look into this just for a moment. As we discussed in set 1, the following are the two main properties of a problem that suggest that the given problem can be solved using dynamic programming. Okay, two main properties of a problem that suggest that the given problem can be solved in dynamic programming: overlapping subproblems and optimal substructure. We've already discussed the overlapping subproblem property. Let us discuss the optimal substructure property. Now, in this respect, the optimal substructure property, I can kind of think about, I think I know what that means. And overlapping subproblems, if that's just subproblems in general, I feel like I can understand what that means as well. Let's just read the AI overviews. In computer science, overlapping subproblems occur when a problem can be broken down into subproblems that are reused multiple times. Overlapping, that's why it's called overlapping, isn't it? Because it can be reused. For example, in the Fibonacci sequence, where each number is the sum of two previous numbers, are subproblems of Fibonacci n. Subproblems of Fibonacci n, right? If you calculate fib 5, you need to calculate numbers less than 5. The next time you calculate fib 4 or fib 3, you can look up the solutions in the table you created. To avoid recalculating the same subproblems, you can use dynamic programming to store the answers. This can reduce the time complexity, blah, blah, blah. So overlapping subproblems, okay, let's read also here. In computer science, a problem is said to have overlapping subproblems if the problem can be broken down into subproblems, which are then reused several times, or a recursive algorithm for the problem solves the same subproblems over and over rather than always generating new subproblems. Yeah, so I can understand what that means. Like, just from the examples that I've seen in the past doing some of these Leetcode problems, I understand what overlapping subproblems are because I can see it as examples in my head. Maybe in a tree, you reach a certain state that within that state has already been processed at some point. Makes sense. Like literally in the coin change problem, that's what we did. We found an overlapping subproblem. Yeah. So a problem is said to have overlapping subproblems if the problem can be broken down into subproblems which are reused several times on a recursive algorithm, or a recursive algorithm for the problem solves the same subproblem over and over rather than always generating new subproblems. Yeah, okay. Now, that's overlapping subproblems. Pretty good. Now, there is also an overlapping subproblems property from Geeks for Geeks. Alright, give me a sec. I'm gonna open the door for mum. Okay. Tabulation bottom up versus memoization top down. Like, what is the difference of memoization? Okay, optimal substructure. In computer science, optimal substructure is a property of the problem that allows an optimal solution to be constructed from the optimal solutions of its subproblems. Yeah, okay, fair enough, that makes sense. It is a key concept in algorithm design and dynamic programming. For example, the problem of finding the shortest path between two nodes in a weighted graph has an optimal substructure. If you know the shortest path from node A to B and from node B to C, you can find the shortest path from A to C by combining the two paths. Optimal substructure is used to determine the usefulness of greedy algorithms for a problem. Greedy algorithms use optimal substructure, but they make choices based on immediate benefits instead of considering future consequences. Sure. In computer science, a problem is said to have optimal substructure of a problem solution if an optimal solution can be constructed from optimal solutions of its subproblems. Okay, again, like the biggest thing to take out of this is what I should write in the boilerplate code. Give me a sec. Let me sit down. Okay. Okay. Let me write about optimal substructure. Sorry. Overlapping subproblems. Optimal substructure. So it was expressed really well when I read this. Overlapping subproblems. No, I gotta find the exact wording. Overlapping subproblems occur when a problem can be broken down into subproblems that are reused multiple times. And optimal substructure is the ability to construct an optimal solution from the substructure. Okay, optimal substructure is a property of a problem that allows an optimal solution to be constructed from the optimal solutions of its subproblems. Epic. And you know, the best resource for this type of topic is Wikipedia. And overlapping subproblems okay. Well, overlapping subproblems, also the Wikipedia article is again very useful. Okay. Like, both of these makes a lot of sense. Alright, maximum product subarray is what we're going to do now. After, I just do a monkey type, because why not? Ooh, not bad. F. Ooh, ooh. Question, exclamation, R. Close. No. I can't get it right. Damn, this is gonna be so awesome. No. Okay. I keep on getting that specific brace incorrect. Yeah, I keep on getting that brace incorrect. Do. Okay, lots of errors. Okay. Wait. That's a tab, isn't it? Tab, 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 tab. Ooh. Not done that before. One E. V. V. Damn. One E7 close times self V dist src 0 spt set false self V for cout in range self V U self min distance dist spt set U true for V in range self. Why does this feel like it's actually taking a long time? Damn. 4 minutes. Alright, maximum product subarray, okay. Coin change, maximum product subarray, let's see. Maximum product subarray. 152. Okay. Given an integer array nums, find a subarray that has the largest product within the array and return it. Within the array and return it. A subarray is a contiguous, non-empty sequence of elements within an array. You can assume the output will fit the 32-bit integer. 1, 2, negative 3, and 4. Interesting. Working with subarrays. Interesting. How can we think about this problem? You can think of it as a backtrack, for example, maybe. So let's think about it in terms of a backtrack first, originally. If you think about it as a backtrack, 1, 2, 3, 1, 2, negative 3, and 4. 1 and 2. Maybe if you just add 1, the choice is you can add 2, or you can add 3, in which case you get a negative number. The largest number you can get. So it's a non-empty sequence of elements subarray. It has to have at least one value, basically. 1, 2, 3. The choice is to include all of them or not. And then at 2, can you include negative 3 and 4? Or you include negative, you include the left side as well. So 1 and 2. Negative 3 included, 4 included. Anyway, 2, 3, 4 And then you have -3, 2, 1, and 4. My thinking there would be go to -3. You can check. The right side of it. So it's worst case n squared still, but you also think that you think about those subarrays. Okay, but if you could possibly have like a tabular subarray, right? Ooh, that actually reminds me. Let me undo closing the tabs that I closed. What was it? Optimal substructure in dynamic programming and overlapping subproblems. This did talk about something interesting. I see. Memoization. Yeah, I see. Okay. I understand. So the technique that we use here, this DP is called memoization. This DP is called tabulation. See more. Whoops. If you try this by basic Kidani, some test cases will pass. Basic Kidani. I will need to search what that means. I will look at understanding what this means. Thank you, by the way, VB. Wait. Like when multiplication becomes 0 or negative, then start with 1. Is that is that Kidani's algorithm? Is it? Am I even pronouncing that right? I don't like the format of this page. I'm inclined to even watch an algorithm, watch an implementation, but maximum subarray problem. Can find the maximum sum of a contiguous subarray with a runtime of O of n. I'm sure there's going to be a solution that Leetcode brings up that talks about Kadani's algorithm. Ooh. Just start from the 0th index of the array. Calculate the running multiplication anytime it goes negative or 0, then reinitialize to 1. Okay. Because we're talking about maximum product subarray. If when you times it with a negative number it becomes a negative number, you make that dp equal to 1. I don't exactly understand why 1 entirely yet. And every time keep updating the maximum. Alright, we'll see. We'll see, alright, we'll see. But I believe you. I believe you, VB. I'm sure you've done this problem before at some point. However, in my case, I'm going to try. Like, I can't even see the recursive approach just normally here. So that's where I'm stuck at the moment. Just see if there's, you know, a backtracking or a, should I say, decision tree approach to this. Is that possible? Backtracking, if it's backtracking, if it's backtracking and you get to a negative number, you can times it with a negative number in the future to possibly get another bigger number. If that's possible. Okay, but that's still not helping me. So I don't know. You don't know DP yet. Interesting. I mean, that's what we're here for, you know? We're learning DP. Alright. Oof. Well, it's literally Kadani's algorithm. And it's an Amazon interview question. Alright, we're just going to have a look now. Have a look at what this video shows. You have a brute force approach, the sliding window technique, and Kadani's algorithm, and a prefix and suffix. I remember something we've done prefix and suffix stuff before. Oof. Alright, let's understand each one of these ways. It's similar to max addition subarray? I believe so. From what I just searched here. Nah, man. I'm not going to try any further here. Just because I want to try, like, actually learning. I can't take too long, man. I can't take too long. That's my policy. Like, if I'm stuck on a problem for 5 minutes and I still can't think of an obvious way, it's just going straight to the solutions.
Hey everyone, welcome back. Let's write some more Leetcode today. Let's look at maximum product subarray. And this is actually a...
Let me turn down the volume actually.
Problem, and I'm going to show you how to solve this problem easily. So we're given an integer array of numbers, and we want to find the contiguous subarray that contains at least one number and has the largest product. So in this case, we have a 2, a 3, a -2, and a 4. And the largest continuous product we can make is 2 and 3 because 2 times 3 is 6. That is the largest product.
How long have you been doing DSA?
Because there's a -2. If we multiply
Probably,
by -2,
it's probably been 3 years now since I first touched DSA stuff.
6. So what's like your first idea how to solve this problem? Maybe brute force, right? Is there a brute force solution to this?
But it's been on and off
A subarray, right? So
in terms of learning.
try every single subarray. So let's say all subarrays starting at 2. We got 1 subarray, 2 subarrays, 3, 4, right? And for each of these, let's just calculate the product, right? Like the first one is 2, the next one is 2 times 3, the next one is 2 times 3 times -2, the last one is 2 times 3 times -2 times 4. And we end up saying that so far the biggest is this, but we're technically not done yet. All of these subarrays contain 2. So now let's look at all subarrays containing 3. So we got 1, right, just 3. Then we got 3 times -2. Then we got 3 times -2 times 4. And basically we repeat this process. Now you can tell that this is not super efficient. The time complexity is big O n squared. For each of these numbers, we're going to end up having n subarrays, and we see that the total number of elements we have is also n, right? It's n elements in the array, so we're going to get n times n is n squared. So my question is, can we do better? And how can we do better? Maybe there's some patterns to this problem that we can use to our advantage to find a better solution than n squared. So let's look at one example. Do you notice anything about this subarray? Well, all elements are positive. So what does that end up doing? Like, this is all positive, so we got a 1. Okay, and next we want to check this subarray. Okay, multiply it by 2. We want to go even farther. Check the 3. Okay, multiply it by 3. And what if we kept having positive elements? 4, 5, multiply by 4, multiply by 5. Do you notice something? Up until this point, our product is going to be a 1. Up until this point, it's going to be a 2. Up until this point, it's going to be a 6. Up until this point, it's going to be a 24. Up until this point, it's going to be 120.
Okay.
We have positive numbers. No matter what happens, they're going to keep increasing, right? So this is the simple case. If we get all positive numbers, then our product is always going to be increasing. So now let's actually look at the opposite scenario. What if we had all negative numbers? Because all positives is easy. You just multiply all of them and you get the max product. But with negative numbers, it's a lot more tricky. So let's look at the first number. So up until here, the max product is just -1. And then we add a second element, a -2. And then what do we get? We get -1 times -2. And we know that the product of that is 2, right? Positive 2.
Yeah.
Now the last subarray we check from all the way from -1 to -3. So we introduce one more value, a -3. And now if we multiply all 3 of these numbers together, we see that our product actually got smaller. Now it's -6. And what's going to happen if we had another
-4
over here? What if we had a -4? Then we multiply by -4, and now we see that our product is going to be 24. So you see that when you have negatives consecutively, the sign is alternating.
Right.
So when you want the maximum, it makes it kind of tricky to have negatives. But we also see that even though we got a -6 over here, there's actually a subarray that has a better solution. If you just take these two numbers, -2 times -3, we get a +6. So why did we get a -6 over here? How can we find the real maximum, which is +6?
Okay.
So even though we're looking
+6.
at product subarray, we're actually also going to need to keep track of the minimum as well, and I'm going to show you why. So first, do you at least agree with me that if we want to find the max product array subarray of the entire thing, it might be helpful for us to at least solve the sub problem, which is the max product subarray of just the first two elements first, and then use that to get the entire one. Okay, that makes sense. We know that the max product subarray of this is 2. Now, if we had a positive 3
So again,
here, then we would say, okay, if I can get the max subarray of the first two
pause. I'm trying to pause. Fuck.
multiply it by 3, I'm going to get 2 times 3.
Okay, fuck. What the fuck? My computer's so slow. This is optimal substructure. That's all I wanted to say.
Get the entire one. Okay, that makes sense. We know that the max product subarray of this is 2. Now, if we had a positive 3 over here, then we would say, okay, if I can get the max subarray of the first two elements and multiply it by 3, I'm going to get 2 times 3. It works when these are positive numbers, but we actually have a negative 3 over here. So I'm going to say, get the max product subarray, which is positive 2, but let's also get the minimum product subarray of these two as well. And what do we know about the minimum? What's the minimum product subarray of these two? It's going to be negative 2. So I'm going to keep track of both positive and negative. So we have a positive 2 and a negative 2. We keep the max and we keep the minimum. So now when we want to compute the max...
Hold on. So the maximum subarray, maximum of this subarray is 2. The minimum subarray of this subproblem is negative 2. Yeah, and the maximum subarray of this problem is, 2. Okay. The maximum product, I should say. The maximum product is 2, and the minimum product of this subproblem is negative 2. Okay.
Subarray, when we include this 3, then we can compute that. We can compute that using both of these values. So
sure, because then we can say we can use the min times by the negative 3 if it's a negative number to get a greater max 6. Yeah, so it's like taking the magnitudes. Okay. For sure. That's the tough one. But I get it. It's the subproblem of maximum product subarrays. Damn. Okay.
So we know that when we take the maximum 2, we get negative 3 times 2, which is negative 6. And we know when we take the minimum, we get negative 3 times negative 2, and that gives us a result of positive 6. So we know the maximum is positive 6.
It's like the magnitude is the important part.
6. So we take positive 6 and put it over here, and we can take negative 6 and put it over here. And hypothetically, maybe we get another element, and this time whether it's positive or negative, right? So in this case, let's say it's negative 4, we will be able to find the solution because the minimum, or rather, we're looking for the max product subarray, and we know if we take negative 4, multiply it by the current minimum, which is a negative number, negative 6, we will end up getting 24, which is what we're looking for. But if you reverse it, what if we had a positive 4 here instead? Well, in that case, we can say, okay, positive 4 multiplied by our maximum, right? Our maximum, which is positive 6. So 4 times positive 6.
24.
We still get it, right? So this
makes sense.
The maximum and the minimum,
Yeah,
we
nahi.
have
That's it.
all the information we need as we continue to add more elements to our array. So now let's just look at one edge case. So we're talking about positive numbers and negative numbers, but we know that one last edge case exists, the dreaded 0 value. Right?
Oh
So what if we
shit,
had a
I didn't
0
even think
value
about
and
that.
maybe some other numbers, 3, 5. Our 0 is gonna kind of kill us, right? It's gonna kill our streak. Like, look what's gonna happen to our min and max.
I did not
6
consider that,
multiplied
damn.
by 0, we get 0. If we take negative 6 multiplied by 0, we get 0 again, right? X times 0 equals 0. And then if we try taking this 0 and making it a product of maybe 3 and 5, it's going to continue being 0, right? Because any number times 0 is going to be 0. So I'm going to decide to handle this in a different way.
Hold on, how could you handle this? Just exclude 0 in your subproblem analysis? Or you break up the subproblems by 0?
So anytime we get a 0 value, I'm going to reset our max to 0, or rather to 1. And I'm also going to reset our minimum to 1. And the reason I'm going to do this is because I don't want to kill our product, right? I'm just going to say that zeros are ignored. We don't really care about zeros. And the reason I'm setting this to 1 is because then when we start introducing new values like 3, it's just going to be 1 times 3, right? Which is
Just gonna
end up being
restart.
3. So 1 is like a neutral value for us. So those are the main things. We want to maintain the max and minimum of our product, and we want to handle the 0 case by resetting everything to a neutral value like 1. Okay.
Shit, wait, let me think. Like, even when you do that though. Whoops, I went back too far. Is this guy just the king of these type of problems? Yeah. He's Leetcode. Leetcode, the man. Real name's Naveed, or should I say Navi? Something else. Navi Singh. Indian tutorial maker, but really, really good. If he has he's making different YouTube videos now. If you actually search his YouTube channel, not bad, but he still makes Leetcode videos every now and then, I reckon. If anything, Leetcode shorts, bite-sized Leetcode problems solved within 30 seconds. Give me a second, I just gotta reply to a message. Hmm. Hmm. Okay. Cool. All right. Let me get back to this. So, my question was, when you reset to 0, the max that you find, you're going to probably keep in another variable. And then you break it off at 0, so everything resets to 1, and then you continue as if the problems were split. Right? That's how you handle the cases. So if that's the case, I could handle it similarly by splitting from every 0, perhaps. And just thinking about the problems. Yeah. What if you just had 0 itself? You would return 0. So the result has to initialize to 0. I think I get it. Okay. If that's the case, like looking at this is pretty good information. Is this an overlapping subproblem? Or is this an optimal substructure? It is definitely an optimal substructure. Overlapping subproblem. Is it an overlapping subproblem? The problem is, yes, it is an overlapping subproblem, but I can't see it in terms of, like, say, a tree where that makes sense. Optimal substructure, yeah. Is it more that if it's optimal substructure, then it's already an overlapping subproblem? Perhaps. No, it's not. So I guess it is overlapping subproblems if you consider it as sets that needs those same multiplications. Yeah, okay. What's an example of a substructure, say an optimal substructure without an overlapping subproblem, for example?
hungry.
Hmm. Is that really a question that I'm asking correctly? I mean, this is something I might want to just clarify with ChatGPT. And problems that are best solved using greedy algorithms. Okay. So this is kind of like this is kind of like a natural follow-up when I get to greedy algorithms. I was just about to ask if you ever used ChatGPT. I mean, you can kind of see my history. Of course I use it, man. Perhaps maybe you don't want to see it all. But yeah, for sure. Why does it differ from dynamic programming? Dynamic programming is needed with when subproblems overlap. In the fractional knapsack. Why does that sound grotesque? Subproblems do not overlap because each choice is made greedily and reduces the problem size linearly, making dynamic programming unnecessary. Fractional knapsack problem. Given a set of items, each with a weight and a value. Given a set of items, each with a weight and a value, the goal is to maximize the total value of items you can carry in a knapsack with a weight limit. You can take fractional parts of an item. What area dev are you looking to go into again? The first time I clicked on your stream, you're doing web dev. Yeah. I'm broadly just looking for a software engineering position. It's not necessarily, I guess, front end or web dev related stuff. I have, like the role that I'm currently at is a software engineering role. But that does include like general knowledge of like front end and back end stuff, I would imagine. So web dev is part of that equation. But maybe not as much as you might think it is, I think. Maybe there's more back end than front end really, even for a software engineering role. How long did it take you to learn JS? Your site looks good. I will say I didn't take all credit for the site that I created. The JS kind of was learnt on the job. I know some parts of it just from like comparing it to Python. I know how to do things in JavaScript by looking at stuff that I've done in Python. Even like Python to JS converters are helpful for me to understand how to use JS. Right? That's how I kind of learnt parts of my JavaScript. But also, the other parts of the equation for, say, the site that I have, it's made from HTML, CSS, and JavaScript, right? But the JavaScript is very minute. There's only a little aspect of the site that is actually JS. The other two is HTML and CSS, right? But those two, the site that I that I copied is one that I copied, and it's the HTML and the CSS there, I just kind of played around with, noticed what elements are what that changes certain elements on the screen, and then, the rest is history. I just figure it out from there. So look, I didn't have any formal education in HTML and CSS. It was just playing around and getting to know the tools, getting to know the languages. How many applications do you think you've sent out this cycle, and have most of them been cold apply? Cold apply. And most of them have been cold apply. I think I know what you mean anyway. I've sent about like no more than 30, I would reckon. And we're talking about this cycle as in when I started back in the start of this year, so around basically around January, right? But yeah, roughly maybe no more than 30 applications. I don't keep track, right? I don't really like keep it in an Excel sheet. So the ones that I pass, or because I probably got stopped at a lot of resume screens. They've definitely, like all of them, none of them were like recommendations from a recruiter or anything like that, right? It was just me applying to that position on their job, on their website. And these are for like various different companies. It's not just big tech. But yeah, it just turned out to be good that one of them was big tech in the end, which I did get, right? Amazon. But, how many passed over into the interview stage? That was basically that was only 3, I think, right? Atlassian, TikTok, and Amazon. Was there anything else? And there was one called Uptick. Right, so there was a smaller one that I did an interview for, which, okay, I did meet them in person. So I did go to like a Hire Fest, which was like an event that had, you just have like quick, like speed interviews with a recruiter, or technically a person from the team, and then you just talk with them about stuff. Talk about your interests. To me, at least, I talked a lot about my interests during that. But it was pretty flexible. There wasn't any like, it was pretty lenient when I did that one. But no, I didn't get that in the end. But I was pretty close. I think that's what they told me, at least. But I think I lacked probably the understanding of the company and asking questions to the company to get to know them more. I think that was the biggest factor in that small company interview. But yeah, like you live and you learn. You learn a lot. You learned DSA in school, right? Yes, I did. Most of it. I think, dynamic programming is one that I lack most understanding from. But now, that's what I'm learning now. And I've been told, like, the subject that I took specifically avoided learning much about dynamic programming. Whereas if you took another one called design of algorithms, that would have actually given you a week of study on dynamic programming. And that would have been slightly better to just know dynamic programming by then. But look, I mean, I've never needed to use dynamic programming until now when I'm learning about it on Leetcode. So, and I'm taking basically about a week to understand dynamic programming as well. It's just diverting that learning experience or that time to learn this concept. Not a big problem. Thanks, Henry, by the way. Tan Nguyen, so when is your onboarding day for Amazon? It's going to be next week. Yeah, literally just next week. It's just going to be the start of next week. It's literally just going to be the start of next week. It's actually quick, man. Scared. Not that scared, but it's cool. Okay, regardless. Fractional knapsack, I don't care. Maximum product subarray. Okay, let's try and solve this now with this idea in mind. Now, you're probably going to have to do this in a bottom-up approach, dynamic programming approach, which is cool. All right. Let's just try it. All right. Dynamic programming, everything starts from 0 or 1 1. Everything starts from 1 1 or 0 0. I'm not convinced. Everything starts from 0 0. Now, if I do the timesing here, it's not going to work. So I need to do the for this in range of len and nums. So we're going to say the max is, yeah, the first value and the min is the second value. But the problem is, should I initialize these to 0 or not? It's a good question. Hello, Akshat. Welcome, man. Okay, so interesting. Let's sit up straight. Think about the subproblems. You can start from 1. And then 1 itself being the smallest subproblem. Say that's the 0th position. The 0th position. The subproblem up to -1 has an answer of whatever. Subproblem up to -2 has an answer of whatever. Subproblem of -3 has an answer of whatever. But once you reach that end, that's all you care about. So from that understanding, the DP only has to be at most the length of nums. However, what is the initialized value within that? Could you have a space optimized version? You might, I think. But anyway, at -1, max and min are just going to be, okay, it doesn't matter what they are initially. They could be like negative infinity, they could be positive infinity. It doesn't matter what they are because they always get overwritten, I think, from my understanding. We'll have to look. All right, so I'm just going to leave it at 0, 0 for nothing in range len and nums. That means it's just going to be at most len of nums. dp of len of nums -1 is what we're going to return. We have the, I guess for I in range of len of nums, I guess, you know, if I'm using len of nums this often, let's just use n to denote len of nums, which means we change in brackets, change in brackets, change in brackets, change in brackets, n, change in bracket, n, I'll just remove this, n, okay. Okay, so for I in range n, why is my computer so slow? I'm so sad. Okay, I in range n. So starting from 0, the subproblem is just 1, or whatever that value is in the first position of nums. In which case, the max and the min is just going to be equal to that. So if I is equal to 0, dp of I is equal to nums of I, right? I agree. And then you would just continue. Now, if it was not 0, it was something else, then if you'd need to use the previous subproblem to solve this subproblem, if nums of I is greater than 0, whoops, greater than 0, let me think. If nums of I is greater than 0, it's a number. dp of I is equal to dp of I minus 1. So I minus 1, okay, yeah, no, that'll be fine, because you've already set the case for when I equals 0. This, you're taking the 0th position. Right, so I also set this wrong, by the way. This should equal to this. Or technically, Could I make it more cool? Doesn't really matter, I guess, but maybe this is clearer for me when I'm looking back at it. So this is equal to nums I also. And nums, okay, of 0, if it's greater than 0, then dpi is this times nums I. And the dp of I of 1, now this is the negative version, dp of I minus 1 1 times nums I so that's still kept as the min. Else you're gonna have, so elif nums of I is less than 0, then you might do the opposite. So I think I know what's happening there. After your first day at Amazon, you're never going to want to use that M1 ever again. That's honestly what I'm thinking as well. Like, I'll stick with this M1 for a while, right? And then by the time I'm back, I'm probably going to be tempted to buy like a new laptop. So, okay, dp of 0 this time. Because it's less than 0, we need to use the negative value. Gosh, that takes forever. Okay. Times nums I. Cool, and that'd be a positive value. And then for when you want a more negative value, you would use the positive value given the negative value. Times nums I. Okay. That's what it looks like. Else. Alright, this is the else case now where nums I is equal to 0. You're saying, by Leetcode's remark, that dpi 0 is going to equal to 1, and dpi 1 is going to equal to 1 as well. Then you're telling me to return dp of n minus 1. Oh, for sure. Right, so that would be you want to return the maximum, so you would return 0. Alright, well, I feel like it's not going to work for some parts of this. 2 is correct there, but not correct here. And why is it that we get negative 24? Let's try and see what this dp looks like during all of these changes. So That's kind of sus. Why is that kind of sus here? I'm going to make it equal to 1, for sure. Then you go to 2. 2 is greater than 0. 1 times 2 gives you 2. And the min is still 2. And then when you get to -3, you're going to be in this spot where your 2 is going to times with -3 to get 6. Would be +6. And then your hold on. Yeah, there should be a 2 times a -3. Oh. You should still take the max of. And then the min of. So max of dpi minus 1, 0. And here. And similar thing here, but for the min. So min of dpi minus 1 of 1. Whoops. Okay. And if we're talking about maxes, let me think. The max of the previous number and this number. Well, if it's positive, it's always going to be positive, right? If it's positive, it's always going to be positive. If it's a negative number times by a positive number, it's always going to be positive. I don't see then how that would be different for if it's less than 0. If you do the max of the previous and the now, and the min of all of that, maybe you don't need it. If it's negative, then you know it's always going to be negative. Okay. So look, if it's negative, it's a number times a negative number, which will be a this is always going to be the case. Just by knowing. The problem is this, I think. So you're saying min dp of I of 1, I think. Sorry. dp of I minus 1. let me think this through. That'll always be a greater number, and the minimum number is always going to be either the previous minimum number or dp the previous minimum number times no, something's not right. Something's not right. The previous minimum number, the minimum between the previous minimum number, and it doesn't need this. It doesn't need this. It doesn't need this. I don't think it needs this. I just changed. Damn. The slowness is killing me. Okay, I'm gonna try just running this. Something's asymmetrical with this. Right, so the output is 8 when you expected 4. So does the 2 there make sense? Because you're saying you get a -3, it's better in this case to just keep 2. Yeah. And the minimum of this would be 6. Yeah. And then you would have 4 in the equation. And when you get 4 in the equation, the best you can do should just be 4. Something is missing here. You're doing 2 times 4 to get 8. Right. When instead, when you see this -3, you can't do anything with that -3. If you have the smallest possible number that you can get is, yeah, -24, that's right. But the largest possible number you can get is not 8, it's 4. So then you think, okay, what's the largest number between 2 This is crazy. This is crazy slow. Hold on. I'm actually just gonna restart this page. Save the bookmarks. Even taking forever to save the bookmarks, by the way, guys. And we're just gonna quit. Okay, I quit. I finally quit. And close this. Close this. Don't save. Exit. Alright, I might go to dinner first. I'll probably be back to do more of this. But no, I want to open this up back again. And then I'll come back and finish this, alright guys? Because I need to eat. Get the brain power to think more about this problem. But I'm close. I think I'm close. It's just stuck on a very... can't get my head wrapped around it issue. Maybe after the dinner it would help. Alright. So I'm gonna eat. I'll be right back. Well, Emma. Alright guys, I just realized I said I was going to the gym with someone else, so I'm gonna have to go to that. We're gonna have to do this problem either when I get back or tomorrow. So the thing is, I might just end the stream now, and yeah, thanks for sticking along. Sorry that it couldn't be more, but yeah guys, thanks for sticking along. Peace.